boat is pulled into a dock by means of a rope attached to a pulley on the dock. The rope is attached to the front of the boat, which is 9 feet below the level of the pulley. If the rope is pulled through the pulley at a rate of 12 feet per minute, at what rate will the boat be approaching the dock when 15 feet of rope is out? To understand this problem, you should think about what's the picture. So here's the water, and above it there's the dock, and some feet away there's this boat approaching, and somebody's pulling the boat through a pulley. So there's a pulley here and there's a rope, and the rope is tied to the front of the boat. Additionally, what's given is that the front of the boat is 9 feet below the pulley. So this distance will be 9 feet. And this rope here will become shorter and shorter. And it's asking for how fast this boat is approaching the dock when this length is 15. So hopefully that made sense. And in order to solve related rates problems, you have to have a simplified picture. So let's try to draw that simplified picture. And my simplified picture is just this, because really the relevant parties in this picture is that this is always 9. This rope is being pulled, so that's shrinking. And to figure out how fast this boat is approaching the dock, you need to measure it by figuring out how fast this side is shrinking, right? Because I'm thinking of this triangle right here, okay? So for this triangle, if this is shrinking fast, that means the boat is approaching the dock fast, right? So this length, which is this, is exactly what we want to know. If we want to know what rate will the boat be approaching the dock when it's 15 feet of rope out, okay? Now, another important thing is when you draw this simplified picture, it's actually a right triangle, you should only put numbers for things that are constant throughout the problem. This length will never change. Even if the boat approaches closer, this distance will always be below 9 feet below the pulley, because the level of the sea doesn't change, right? And therefore, we put 9 here, that's a constant. On the other hand, the rope will get shorter, this distance will get shorter. So we have to assign variables in that case. I will put z here for the hypotenuse, because I have a habit of putting z for the hypotenuse. But you can put other letters here. You can put x or y or a or whatever. And because this side is the horizontal distance, I'll just put x. Okay, so given this right triangle, let's see what's given. The rope is being pulled at 12 feet per minute, right? So we know that dz dt is shrinking, so I'm going to put minus. Rate of change of this z is negative 12 per minute. And because we want to know what rate the boat will be approaching the dock, we need to know the speed of the x. So the question is, what is dx dt when? And then I said when because this is when, right? So in these related rates questions, it's really important to notice this when or at, because any number that appears afterwards, you shouldn't be using that at the beginning. You should only use that way at the end, okay? At least you should hold off using this number after differentiation, okay? So if you're done with derivatives, you may use this number, but this number should not be used in the beginning of the problem, okay? So what is that? When z is 15, the question is, what is dx dt? That's the question. And that already captures everything that's written here. So the numbers are there, right? 9, 12, 15 are there. And it's basically exactly the setting that we need. But in order to relate the rates of z and x, you need to know the relation between z and x. So what do? You use something. Well, that something in this case is it's a right triangle. It's a single right triangle. What can you do other than the Pythagorean theorem? So we just write down the Pythagorean theorem and done. Really, now that this equation captures this picture, we have a relationship. The only thing now that's needed is these three equations. These two things are given, and we're looking for that. Okay? So at this stage, you can probably just forget about what it was. You can forget about this complicated picture. You can even forget about the triangle because we already have this. Okay, so what's our next step? Because this relationship between x and z has to be turned into a relationship between the derivatives, we have to differentiate this. So let's differentiate it. X squared plus 9 squared equal to z squared is differentiated, differentiated, differentiated. Now, because these derivatives are derivative with respect to time, it means that z and x are both functions of time, which makes sense because as time goes on, this length will get shorter and this length will also get shorter, right? So they do depend on time. And because these are derivatives with respect to time, when I differentiate, I better be differentiating by t. So see, this Newtonian notation is convenient, but it's often ambiguous, and you have to ask yourself what you're doing. And if you write in Leibniz notation, which is the same thing but in a different notation, actually tells you exactly with respect to which variable you're differentiating by. So it's very useful. Okay, so just keep in mind that we're differentiating by t, and that has immediate consequences to the derivatives here because x has to be thought as a function of t because after all we're differentiating by t, and because x of t, x which is a function of t, is nested inside the square function, when you have nested functions you must use chain rule, right? So we have to use the chain rule, which states that first differentiate the outside function, so differentiate x squared, which is 2x, and then since x of t is the nested function, or another name for nested function is the inner function, right? So the inside function. The inside function has to be pulled out and you have to differentiate that. So we're going to differentiate the inside function by t. How about 9 squared? Well, although 9 squared look very similar to x squared, they're totally different because 9 squared is a number. That's 81. That's a number. If you differentiate a number, that's 0. For z squared, again, z is a function of t nested inside the square function. So if you differentiate, this is the derivative of the outside function is 2z. When you pull the z outside and differentiate by t, this is what you get. Okay, keep in mind that our goal is to find dx dt. So we have to isolate dx dt by dividing by 2x both sides. And the result is that dx dt is equal to 2z over 2x dz dt, and 2 cancels. That leaves you with z over x times dz dt, but dz dt is given here, it's negative 12, right? So that's negative 12. So we see that dx dt is negative 12 times z over x. Okay, dx dt is negative 12 times z over x. Now, was this what we were looking for? Well, not quite. We were looking for dx dt when z is 15. Now keep in mind our picture. We do have to go back to the picture to see what's going on. I said that you don't have to remember it, but if you go back to the picture, this was 9, this is x, that's z. If z value becomes 15 and this is 9, then Pythagorean theorem can be used to figure out what this length is, right? So we can use Pythagorean theorem to figure out when z is 15. When z is 15, x squared plus 9 squared is 15 squared. So x squared is 15 squared minus 9 squared. And that's 225 minus 81, that's going to be 144. Taking the square root will give you 12. Okay, great. So that means now dx dt, when z is 15, is equal to negative 12 times z is 15. And when z is 15, x is 12. So I see that 12 cancels, and you're left with negative 15. And then it's a rate of change, so this is a feet per minute. See, the unit for the time in this problem is minutes, and the unit for x in this problem is in feet. So that's what you have, and the purpose of this minus is to make us realize that this distance is shrinking, but since it was just asking for how fast the boat was approaching the dock, in the answer you shouldn't have the minus one, so the answer should be 15 feet